Hey, let's review the backend portion of this blockchain and cryptocurrency project. Now, if you decided to fast track to the front end portion of this project, this is going to be the perfect way to get onboarded with the material that appeared on the backend. Of course, reviewing the code yourself is a must as well, but this will help build an overall picture. So on the other hand, if you did complete the backend part of this project, feel free to skip this video or stick around as it's a nice way to wrap up and review the learnings. All right, let's start this whirlwind tour of the completed backend of this crypto chain project. So overall, recall that we developed this core blockchain application through test-driven development. This means that our backend is now reliable and robust in terms of being able to accept new changes and inform if currently expected behavior has been affected. So let's begin in the initial blockchain/block.js file. This is the literal building block of the entire blockchain. So it has an initial structure of a timestamp, last hash, hash, data nonce, and difficulty field. The difficulty and the nonce field were created for a proof of work system to account for how quickly new blocks could be created. We also have this concept of the genesis block, which is an initial dummy block of the blockchain with hard-coded values, so this allows the blockchain to get going. As the first real blocks are added in the mine block function. This do-while loop is particularly important for the overall proof of work system. Now to create a block, we have a little cryptographic security in place through the hash method, and we implemented the hash method through a cryptohash.js implementation. This method will take in any number of inputs. It will sort them. It will stringify those inputs to track any changes to objects, and then it creates a unique hash based off of that. Now, if any character in those inputs change, then a new unique hash is going to be generated. Overall, this allows us to link blocks together in a blockchain class. So we have this blockchain/index.js file. This blockchain collects multiple blocks together in a chain array. Now, a key piece of this is that every block's last hash field must be set to the hash of the previous block, which is why when we add a block, we pass the last block reference. This creates the links between each block. Now, storing the blocks itself in the array is not so complex, but chain validation is something way more involved while also being highly crucial. The blockchain's power comes through allowing multiple blocks to interact with each other, and a huge part of that is validating blockchains contributed by other users. So this chain validation primarily involves two checks. If you scroll down, you're going to find the isValidChain method. And in here, the last hash of each block must be actually valid. Now there's also a difficulty requirement for each validated hash based off of a leading 0 bits implementation for the crypto hash. And finally, the generated hash field based off of all the chain fields itself, or rather the block fields, must be correct according to a validated hash. These checks together make sure that a generic blockchain looks good. No one can break the hash linking. And likewise, no one should be able to tamper with the data, timestamp, or hash without breaking this generated hash validation. But there's also the huge piece of the transactional data to validate as well. That aspect came in when we built the cryptocurrency section of the project. So with validated chains, we also have the concept of chain replacement. We captured that with the replace chain method. If an incoming chain is longer than the current stored blockchain array and it's valid, well, it's time to replace the current stored blockchain array with the incoming one. So the overall system works on multiple nodes agreeing on the longest version of the valid blockchain. The longer the blockchain gets, the more powerful and hard to defeat this system becomes. Again, a huge part of this is the proof of work system that we implemented within the block.js file. Notice that we have a mine block function, and mining is an analogy for doing that proof of work and spending the CPU power to find a valid hash to add a new block. So this valid hash, as mentioned before, must meet a difficulty requirement. And the requirement is that there is a certain number of leading 0 bits when it comes to the actual hash value. Notice that the difficulty in the system adjusts as well. And this is to overall achieve averaging the rate at which blocks get mined in the system to come close to a set mine rate. That way, by raising the difficulty, we can slow the miners down. And by lowering the difficulty, miners can find valid hashes more quickly. Overall, this proof of work system helps prevent what's known as the 51% attack. So the 51% attack is this scenario where one blockchain node in the overall network has a majority of the computational power. They only need 51% to have the majority. And with that power, they can take over the blockchain by building a chain in their favor, but nonetheless valid. And since it's valid and longer, every node will have to accept the chain. But this proof of work system makes it ridiculously computationally expensive to attempt such an attack. Plus, the point is, if an attacker wanted to undermine a system where they could profit even more by keeping the system strong and healthy, why would they even make this attack in the first place? Okay, with this core logic for the blockchain down, we then allowed the blockchain to be interactable via the API in the main index.js file of the project. We configured a GET request to get the blocks. There's a POST request to mine a new block to the blockchain. You can also conduct transactions to the blockchain. And overall, there's also this pub/sub implementation to make sure that transactions are broadcasted as has happened, and also that blocks are broadcasted as they're added to the blockchain. Cool. So this pub/sub class itself follows a publisher-subscriber paradigm for passing messages between servers. So rather than an implementation that would have to keep track of the addresses of every single blockchain peer in order to communicate, the pub/sub implementation has a lot less overhead. It works by having channels where subscribers listen for messages and publishers can broadcast their messages. Currently, we have a relevant blockchain and transaction channel, as well as an unused test channel. But this has been coded in such a way where we can easily add new channels and related broadcast methods and message handling capabilities for any new functionality that we want to add to the system. So back in the main index.js file, we also added this logic to make sure that we could start up peers through this generate peer port functionality. That way we can have multiple instances of the blockchain application. Okay, then we graduated to the overall cryptocurrency, which started with a wallet/index.js file to make a wallet class. The digital wallet is a way to allow multiple users to interact with each other in the cryptocurrency. The wallet's primary function is to hold the all-important key pair, which contains a private and a public key. The public key can be used as an address to receive currency on the system. The private key, on the other hand, must be kept secret. By using the private key in the key pair, the wallet has the capability of generating unique signatures for data. Note that getPrivate, unlike getPublic, is refrained from being used, because we don't want to introduce any blatant code paths where that can be leaked. Next to wallets, we have another key piece of the cryptocurrency, which are the transaction objects. And these are official records of the exchange of currency between two wallets. There's an input field as well as an output map. The input map contains an official signature from the actual sender wallet, and the output map contains any values that were conducted in the transaction. So there's one value for the recipient, and then as well as any other values for the recipient in this update function. And most importantly, there's a remaining balance for the sender wallet, which records that sender wallet's current balance once a transaction is official in the blockchain. Now, as multiple users start contributing these transactions, we collect that data in a structure called the transaction pool. This has an inner transaction map, and this can set transactions, update existing ones in the same code path, or even replace the entire transaction map if it needs to. Another key object in this is the transaction miner. And the transaction miner does the important job of getting valid transactions from the pool. It also has a special reward transaction, so they're not doing all this mining work for free. They're hoping for currency by finding the valid hash that consists of the valid transactions. Then it adds a block to the blockchain, it'll broadcast its chain, and then clear its local transaction pool. Okay, with transactions also recorded in the blockchain, this allows the wallet to keep track of an accurate balance. So in the wallet/index.js file, notice that we have this calculate balance method. So the idea is that the balance at any point in time is the output amount for that wallet at its most recent transaction, in addition to any output amounts that it received in the blockchain history after that most recent transaction. Finally, we wrapped up the backend by validating the blockchain transaction data. So in this blockchain/index.js file, we have this huge valid transaction data method, which enforces 4 main rules for the cryptocurrency. 1, when it comes to a block of transactions, there shouldn't be duplicate minor rewards in the block. 2, the transaction should have a valid shape overall, which we're enforcing with the valid transaction method, meaning its input signature should be good and its output map should be formatted correctly with an output total that matches the input amount. Note that this also means that minor rewards should have the correct mining reward value as well, which we have in this check right here. 3, the input balances must be valid and correct according to the blockchain history. And 4th and finally, there shouldn't be any duplicates of an identical transaction within a block. And that's what we accomplished in the blockchain backend. I know that I said that this would have been a whirlwind tour at the beginning of this video, and this video might have taken a little longer than you expected, but it's a testament to how much we truly accomplished while building this blockchain backend. And we didn't even go over all the testing files that we also built. Again, give yourself a huge pat on the back for developing this project. Or if you use this video to fast track to the front-end portion, then hopefully you have a nice grasp on the code and concepts that are contained in this blockchain backend. And on that note, be sure to watch, or rather go to the next lecture, to make sure you set up the blockchain backend properly so that you're prepared to develop the front end. Okay, with this review done, let's move on to the blockchain front end.